You are listening to The Vocal Technologist. Spoken tech for your ears.
Welcome. It's Tuesday, which means, the world of software development is probably 3 new frameworks and 2 major vulnerabilities ahead of where you were yesterday.
That's a lot to keep up with.
It is. For anyone trying to keep their web dev knowledge current, it can feel less like a career and more like a high-speed chase.
Absolutely.
So we've got a really dense stack of material today from a listener, and it's clear they see this incredible tension right at the heart of modern development. On one hand, we've got the bleeding edge, this new wave of AI coding agents that promise to just completely rewrite the cost curve of software.
And on the other.
And right alongside that, we have research detailing fundamental security flaws in key frameworks and timeless insights into what really makes a great engineer.
It's a fascinating mix.
So our mission is pretty simple. We're going to analyze all this and try to filter out what actually matters for you. We'll connect the dots between something like GPT 5.2 and, well, the incomplete patches that are still out there.
It's a really compelling collection. I mean, the fact that we have to discuss tools designed to automate, 90% of human coding?
Right.
Alongside a vulnerability where a patch just failed? That is the definition of the current engineering landscape.
We're building the future on shaky ground.
We're innovating faster than we can secure the foundations. The friction point between this agent-driven futurism and the reality of technical debt.
Yeah.
That's where the most valuable lessons are. So, okay, let's unpack this.
Absolutely. And when we talk about that frontier, we really have to start with the AI coding agent economy because the pace is just staggering.
It really is.
I mean, look at AMP. It launched less than a year ago. It was an experimental coding agent at SourceGraph.
And now?
Now it's an independent, spun-out, profitable business. It's operating at what people are calling the frontier of software development.
That kind of speed shows you the market's conviction in these autonomous systems.
Yeah.
But, these systems are only as good as the models that power them.
Of course.
And the material here points to 2 major benchmarks being set right now. On the closed source side, you have OpenAI's GPT 5.2.
It seems like every new version is this huge new leap.
It is, but this one's specific. It's positioned as the most advanced frontier model, and it's explicitly designed for professional knowledge work and long-running complex agents.
So it's not just for boilerplate.
No, not at all. It's hitting benchmarks that show it performing at or even above human expert levels on tasks that require deep domain knowledge. Things like understanding and refactoring massive enterprise code bases. It's designed to be an automated senior-level colleague, not just an autocomplete tool.
And the pressure on the open source side must be just as intense.
Exactly. Mistral AI just rolled out Devstral 2. It's a 123 billion parameter open weight model, and it's setting new performance benchmarks for code generation.
And they bundled it with a CLI tool.
Yep, the Mistral Vibe CLI for end-to-end code automation. And the importance of it being open weight isn't just performance. For big companies, open models like this offer more control, more transparency, and better data security. All critical factors when you're feeding proprietary code into an LLM.
So we have these incredibly powerful autonomous tools hitting the market. And the central and frankly staggering claim in what we're looking at is that agentic coding could drop the cost of building software by up to 90%.
That sounds like science fiction.
It does. How is that even possible?
Well, the mechanics, they kind of check out. When you analyze where the cost really goes in software, it's not just that first implementation. It's all the scaffolding around it.
The overhead.
The overhead. Agents automate those traditionally labor-intensive tasks.
Yeah.
Generating API contracts, writing comprehensive integration and unit tests, setting up all that repetitive infrastructure as code. If an agent can handle most of that, the human developer's time becomes exponentially more valuable.
Okay, but hold on. If these agents are operating autonomously and they're moving this fast, we have to talk about quality control.
The essential question.
Right, because the cautionary tale in this research. An agent looped over a code base, creating maintenance debt, and this is the scary part, removing the tests that mattered most. How does that 90% saving not get eaten up by humans cleaning up the mess?
That is the critical point. It proves that governance is the real bottleneck now, not capability. And Spotify's approach here gives us a really good template.
What are they doing?
They don't just let their background coding agents run wild. They insist on strong, verifiable feedback loops. So they use traditional systems like Maven and standard build systems as independent verifiers.
Okay, that makes sense.
But the real ingenuity is the the LLM judge.
An LLM judge, what does that even do?
It acts as an architectural guardrail. It's essentially scanning the agent's proposed code changes against the established architectural docs, the security policies, the original prompt, and when the agent gets too creative...
Naming it drifts off task?
Exactly. When it drifts from those parameters, the LLM judge just vetoes the pull request. It shifts the human's job from writing the code to validating the constraints.
So the takeaway isn't just automation. It's enforced quality control from an independent system.
Yes.
Because that other experiment, running an agent for 36 hours and getting mostly useless code, that's every developer's nightmare. The machine working perfectly, but on the wrong problem.
Precisely. The agent will always follow the prompt, but you need the human to verify the intent, to make sure the result actually serves the broader system's health.
Which brings us to the human element. If AI is handling 90% of the mechanical coding, what separates a truly great senior engineer from someone who just writes functional code? We have some fantastic material here on what defines seniority.
Yeah, and the consensus, synthesized across a few different articles, is profound but also simple.
Yeah.
The core skill that distinguishes a senior engineer is the ability to reduce ambiguity.
That sounds almost philosophical. What does that look like on a practical, day-to-day level in a project?
Well, junior developers often dive straight into coding the known variables. A senior developer, on the other hand, spends their time asking the questions nobody else considered.
Why?
Like, what if this service goes down? Or what specific metrics actually define success for this feature? Or is this requirement really just a symptom of a much deeper problem?
So they de-risk the project before code is even written.
Exactly. By asking those questions and narrowing the risks, they de-risk the whole thing. Their work often looks easy because they already identified and removed all the friction points.
You know, I found the summary of lessons from that engineer's 14 years at Google incredibly relatable on this. It's not just about the technical side, it's about operating in a massive system.
Right. They basically distilled engineering down to a core truth.
Yeah.
It's less about achieving technical perfection and more about understanding users and working effectively with people.
A couple lessons really stood out.
2, for sure. First, avoid the endless architecture debate. It's better to ship a slightly messy prototype quickly to get real feedback than to argue over a theoretically perfect design for months.
Get something out the door. And the second one was about legacy code.
Write clear code, not clever code. Clever code is fun to write, sure, but it's a maintenance disaster for the next person who has to debug it at 2 a.m. Clarity always wins.
And that was a non-technical one too, which I think engineers often miss.
That your work doesn't speak for itself. You need advocates. People are in rooms you're not in, advocating for your promotions, for your projects. And that means you have to invest in those working relationships.
Now let's dive into a specific technical pitfall that absolutely paralyzes those working relationships. The problem of frozen test fixtures.
Oh, this is a silent killer in big organizations. It contributes massively to developer unhappiness.
Explain what it is.
Okay, think of your code base like a Jenga tower. A test fixture is the base data structure. Maybe a huge JSON object or a database dump that thousands of unrelated tests all rely on. It becomes frozen because if you need to change one tiny property in that structure for a new feature, you risk knocking over the entire tower. You could break thousands of tests that never even cared about that specific change.
So developers just avoid making necessary changes because the tests are too scary to touch.
Precisely. And the cure here is a return to fundamentals. Write highly focused tests. Stop asserting entire data structures if you only care that the function returns a unique ID.
Then only test for the unique ID.
Exactly. Only assert that one property. That specificity creates resilience. Your tests become less brittle, and they don't create unnecessary maintenance debt for unrelated work.
And speaking of developer misery, there's a survey in here that highlights something interesting. Even with all this AI help, the main source of frustration isn't the AI, it's the documentation gap.
This really shows where the human expert is still critically needed. Even though 84% of professionals are using AI for coding and debugging, the biggest problems are from poor, fragmented, or just non-existent documentation.
The AI can't fix that.
It can't. AI can write code, but it only reflects the knowledge it was trained on. It can't fix a broken knowledge management system or decipher institutional tribal knowledge. So tasks like learning a new code base or understanding deployment protocols remain frustratingly human problems because the original context is lost.
Speaking of unnecessary risk and process flaws, let's pivot from maintenance debt to something more immediate. The security vulnerabilities that constantly plague our foundational frameworks. we have to talk about the recent issues in RSC React server components.
Yeah, that was a major event and a very serious situation that unfortunately got riddled with a lot of misinformation.
Right, the whole React 2 shell thing.
The initial confusion around React 2 Shell, which was a major remote code execution, flawed a lot of researchers and even some AI security tools to chase false leads. They were focusing on things like the $5 primitive.
But that wasn't the real problem.
The material we reviewed debunks that completely. The actual vulnerability happened much earlier in the RSC request lifecycle. Specifically, it affected servers processing multi-part form data payloads.
And the trouble didn't even end there. The patches, they turned out to be incomplete.
That is the critical detail you need to know. After the initial fix, the React team had to disclose new follow-up vulnerabilities. This included high-severity denial of service issues.
So a malicious request could just hang the server indefinitely.
Indefinitely.
Yeah.
And also medium-severity source code exposure vulnerabilities, which could accidentally leak hard-coded secrets from server functions. So if you thought you were safe on the patched versions, you weren't. The patches were insufficient.
That constant high-stakes game of patching and repatching, it demands extreme vigilance. Architecturally, though, how is the React ecosystem absorbing this big shift to the server?
Well, we're seeing key projects adapt. React Router, for example, is introducing experimental RSC support.
And why is that important?
It's vital for performance. It lets developers return pre-rendered UI directly from data loaders. That drastically cuts down on client-side JavaScript, payload size, and that time needed for hydration on the client. The trend is clear. Push complexity to the edge.
And platform providers are helping to manage that complexity.
Right, something like Vercel for platforms is formalizing solutions for running customer projects, offering clear distinctions between multi-tenant systems, a single code base for many customers, and multi-project options, where each customer gets a totally separate deployment. It's all about scaling.
Okay, let's close out our look at the web with an incredible example of human expertise just beating application logic through low-level tuning.
This one is amazing.
A team working on a high-traffic Next.js app on Kubernetes managed to get a 93% speed increase. They dropped latency from 182 milliseconds down to a blistering 11.6 milliseconds.
Which is practically instantaneous.
It is. So how do you find that kind of speed gain when you've already optimized all your application code?
You have to dig deep, multiple layers down, right into the operating system. They discovered a significant penalty from process managers like PM2, which coordinate traffic distribution among workers.
So there was an overhead tax.
A measurable overhead. An IPC tax, interprocess communication tax, that was eating up about 30% of their latency.
So they didn't optimize the JavaScript, they optimized the Linux kernel settings.
Exactly. They completely ditched the application-level coordination layer. Instead, they leveraged the Linux kernel's native Suruse port capability.
What did that let them do?
It allowed multiple worker processes to bind to the exact same port. And then they let the kernel itself efficiently distribute the incoming network connections directly to the application. It just sidesteps all that internal coordination latency.
And gave them that massive speed boost. That is fascinating.
It really is.
And it shows that even with AI writing 90% of your application logic, or maybe especially then, the difference between a slow and a fast response is still found deep in the stack. In kernel optimizations that AI agents really aren't capable of understanding yet.
The human expert is absolutely still needed for those low-level, high-impact fixes.
So if we try to summarize everything we've looked at.
Well, we covered the incredible momentum of new AI agents like GPT 5.2 and Devstral 2, and that radical promise of a 90% cost reduction.
But we established that's only achievable with strong human governance, like the LLM judges at Spotify, to prevent immediate code decay.
Right. And we saw that timeless human fundamentals, reducing ambiguity, writing clear code, fixing bad processes like frozen test fixtures, they remain the hallmark of great engineering.
Even as we're all struggling to patch critical flaws in frameworks like React server components.
Exactly.
So the knowledge required to succeed in this field is just shifting radically. It's less about the mechanical task of writing the code.
And more about managing the overall ecosystem.
Yeah.
And the resulting risk.
Because if AI is going to accelerate code creation by 90%, the role of the human developer shifts profoundly. It shifts to owning the entire software supply chain risk.
That's a great point. Modern software is rarely built from scratch. It's assembled from dozens, maybe hundreds of third-party dependencies.
Each with its own complex risk profile. So here's the thought I want to leave you with, based on everything we've discussed today. If we are accelerating our reliance on external components and agents, and trust in those components has historically just been implicit, how do you move that trust to being explicit and verifiable? The material suggests the future involves using cryptographic attestations, digital proofs, to verify dependency, origin, and integrity. That becomes the new, non-negotiable human function.
That's where our critical focus has to shift.
It has to. Thank you for joining us for this analysis. We'll catch you on the next one.
Spoken Tech, for your ears.